All right. Next problem. Now we have, it says here, one diagonal of a square EFGH is shown on the coordinate grid. We need to choose the correct options to fill in each blank. For each blank, fill in the circle before the option that is correct. All right. Let me go ahead and make this just a little bit smaller. Hopefully, maybe. All right, I think that's pretty good. All right, so here's what I want you to remember about the diagonals. You got to think back. I know this is taking you back to just before Christmas break, I believe. Man, that seems like a long time ago. But the diagonals of a square, okay? Diagonals of a square. There's basically three characteristics. One, they're going to be congruent. Okay, the diagonals will be congruent. Two, the diagonals are going to be perpendicular to each other. Okay, they form a 90-degree angle to each other. And number three, they bisect each other. Okay, so they cut each other in half. So here's what I'm going to do. The location of point F. Okay, let me think here for a second. The location could be at the following points because the diagonals are, okay. So basically, this is a diagonal right here, and we want to figure out where one of the other points of this square could lie. So I'm going to go ahead and do this. I'm going to find the midpoint of this, segment right here. If I go up 1, 2, 3, 4, over 1, 2, 3, 4, 5, 6, 7, 8. If I go halfway up that, 2, and over 4, there's my midpoint, okay? It's halfway up and halfway over. Now, from there, go ahead and make that the midpoint. I'm going to go ahead and perpendicularly bisect that. So if this is a rise of 2 and a run of 4, so the slope of EG has a rise of 2 and a run of 4, the slope is basically a 1 over 2 slope, okay? So I'm going to go ahead and extend this in a perpendicular manner. So the perpendicular slope to that is going to be a negative 2 over 1. All right. So if I go down 2 over 1, down 2 over 1, up 2 over 1, up 2 over 1. Okay. If we look here, let's see here, up 1 over 2, up 1 over 2, that'd be the midpoint. So we're going 2, yep. All right, so this diagonal right here is the same length as that diagonal right there, and it's being bisected perpendicularly. Okay? And so if I connect these endpoints, you should hopefully start to see the square that we're looking at. Okay? So there's the square. Obviously, if you can be a little bit more accurate with your straight edge, you're going to see it a little bit more clearly. So F has to either lie here or up there in one of those two locations. So as we look through this, negative 3, 4, negative 3, positive 4, we're up in there, that doesn't work. Negative 1, 6, negative, oh, I did that wrong, didn't I? Negative 3, 4, 1, 2, 3, 4, doesn't work. Negative 1, 6, that one does work, so that could be a possibility. Obviously, that's the correct answer. And then 1, negative 8. 1, negative 8 obviously doesn't work. Okay. Now, what's nice about this type of problem, and I hope you take this to heart here, and that's this. You could have not known what I just covered as far as the diagonals here, but you probably still could have figured out the correct location of F. If I go ahead and graph those 3 points that are listed down here, negative 3, 1, 2, 3, 4. There's the 1, okay? Here was the other one that we talked about, okay? And then here was the last one, okay? Obviously, if you're gonna, if you have some understanding of what a square is, this isn't going to end up being a square because the two side lengths aren't the same, okay? So if I go ahead and get rid of those two, all right? If I go ahead and do this, I think you can pretty much see that these two side lengths aren't the same, okay? And so as a result, this is the only possibility just by looking at it. You didn't have to know all that background information. Now, you do need to know the background information for this, and this is one of those problems that, again, has an error in it. Because the diagonals of a square are congruent, and, so we've got that, okay, and, well, it's a parallelogram. They have to bisect each other. So this one should be filled in, okay, and they're perpendicular. There we go. Okay, the diagonals don't have to have the same slope, otherwise they would never intersect, and therefore they wouldn't be diagonals. Okay. All right, so hopefully that all made sense to you there. All right, now looking at the next one, let's go down here. All right, now the next problem, here's what we have, number 14. We have a polygon, and we have to, in the coordinate grid, and what's the perimeter of the polygon? Nearest hundredth of a unit. Now, I'd really make sure I've got this down, because if you're entering this into an answer grid, obviously you could probably go ahead and put them, you could put it to nearest tenths, you could put it to nearest thousandths, 10 thousandths, even, let's see, 10 thousandths would be the most that you could probably, well, now you can even move out even further. So you, 100 thousandths, probably how far you could put it. So you want to make sure that you're accurate here with what they're asking, nearest hundredth place, 2 places after the decimal. Now, how am I going to do this? Well, we've done this problem in the past, okay, earlier this year. 1, 2, 3, 4, length of 4. 1, 2, 3, 4, length of 4. Now, how do we figure out these other lengths? I'm going to go ahead and form a right triangle. I'm going to figure out that length. This is length of 1. This is length of 1, 2, 3, 4, 5. So the length of AE, I'm going to go ahead and do 1 squared plus 5 squared is equal to AE squared. Okay, so 25 plus 1 is 26. I'm going to square root that, AE. Don't have to simplify the radical because it's not asking for it in simplest radical form. It's asking for it to the nearest hundredths place. This one right here, okay, I've got 2 and I've got 3. This one down here, I've got 2 and I've got 3. These 2 triangles are congruent. It's just been rotated. So I'm going to go ahead and say that there are 2 of them here. So for BC squared is equal to 2 squared plus 3 squared. Again, I'm using my Pythagorean theorem here. Okay, square root of 13. And we know that CD will have that exact same length. Okay, so as a result, if I go ahead and add this all up, the perimeter will equal 4 plus radical 26 plus radical 13 plus radical 13. The one big thing here, make sure when you're plugging this into your calculator that you're stepping outside of the radicals there. You're not having it so it looks like this. Okay, we don't want to do that. We want to make sure we're taking the square root of just 26, the square root of just 13, and the square root of the other 13. Okay, so again, you should get 20.13 or 31 nearest hundredths place. You can go ahead and look that over. Make sure that that is correct or how you've done it within your problem. Okay. All right. The next problem. Let me do this here. Okay. If you look at the different labeling, the nice thing, this is the only problem I think we really taken advantage of when using the computer as opposed to strictly paper pencil tests. Because you kind of have to imagine what's happening between the scenes, where on a computer you see all the scenes. So what will be the result of Rubin's construction? If you don't remember how to construct a perpendicular segment, a bisector of a segment, or to construct congruent angles, then you might want to look back at the video that I posted online that you guys did over spring break, or were supposed to have done. Again, this is a very simple problem if you just look at what's going on. And so I really hope that everybody gets that one correct. That's really all I have to say about that problem. All right. The next problem. number 18. Okay. Or I'm sorry, number 16. I guess I got ahead of myself. Number 16, this is the one problem I was telling you in my very first video, that you want to make sure that you put the volume, you understand what the volume formulas are. So it says here, as phosphate is mined, it moves along a conveyor belt, falling off the end of the belt into the shape of a right circular cone as shown. Now, what does that mean, right circular cone? I'm not sure why they feel the need to put a circular base to it, because we know all cones have a circular base. But the right portion means this, that the vertex is directly over the middle of the base, and it forms a right angle. Okay, so that's why we have a right circular cone. A shorter conveyor belt also has phosphate falling off of the end into a shape of a right circular cone. The height of the second pile of phosphate is 3.6 feet shorter than the height of the first. The volume of both piles is the same. Find the nearest tenth of a foot. To the nearest tenth of a foot, what is the diameter of the second pile of phosphate? Okay. So back on the very first page, your reference sheet, you had this formula, 1/3 base area times height. Okay, and that's for a cone. Okay, what's the base of a cone? Well, the base is a circle. So your formula for a cone is actually 1/3 pi radius squared height. Well, if I go ahead and figure out the radius here, which would be half of 48.6, 24.3 feet is what we're looking at there. Okay, so if I go ahead and plug this in, I have the volume of the one cone, 1/3 pi, 24.3 feet squared times the height. Now again, the height is how tall the figure is, which is 15.3 feet. Okay, that should equal the volume of the second cone. We just don't know what the diameter of the second pile is. So if I do this, 1/3 pi, we don't know what the diameter or the radius will be. Okay, and then the height of the second cone is what did it say, 3.6 feet shorter. So if I take the 15.3 and minus 3.6, that gives me 11.7. Okay, that's the height of the second cone, so I'm going to plug that in right there. Okay. All right, now from there, here's what I can do. The 1/3 is on both sides of the equation. They're going to cancel each other out. Divide through by 1/3 cancels out. Pi's, they're going to cancel each other out. Okay. So if I go ahead and square 24.3 and I multiply that by 15.3, I get this, 9,034.497. Okay. And again, that's equal to 11.7 times the radius squared. Now, from there, order of operations tells me I have to divide before I square root. Okay. Remember, order of operations in algebra is backwards. So if I divide by 11.7, okay, I end up with 772.2. Sorry, that got sloppy there. Equals the radius squared. Okay. Now, to get the radius length, I'm going to square root both sides. So I get the square root of 772.2. Okay. That's my radius length of this secondary cone. Now, we know the diameter is twice as much, so if I go ahead and take the diameter, I'm going to double this. Okay? And what you will get when you plug that into your calculator is 55.6 feet right there. Okay? So again, that's more of an algebra problem, but it's kind of asking, do you understand the formulas that we've been working with? Again, this is not one that we've covered. It's the only one that I've seen that deals with volume. Hopefully there aren't a lot, but hopefully you'll understand how to manipulate those equations to get the answers that we're looking for. All right, so next one. All right, a proof, yes. All right, here we go. It's actually a very simple proof. So here's what we're going to do. AD bisects angle EAC. EAC. So I know that this angle is the same as that angle. That's what I would mark out initially. Okay. I also know that angle FDA is the same as angle BDA. Now what you should be thinking to yourself right now is we're one step away from proving the triangle's congruent. Okay? So it says there are 3 blanks in the proof below. Choose the correct option to fill in each blank. For each blank, fill in the correct circle before the option that is correct. It is given that AD bisects blah, 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 blah. Since AD bisects angle EAC, we know the 2 angles are congruent, which we marked out initially. From the definition of angle bisector, we know that AD is congruent to AD by the reflexive property. Everything's easy so far. And as a result, I'm going to go ahead and mark that down right there. We know the triangles are congruent by, which down here it says angle side angle. The difficult part of this one is matching up the correct triangles. I know still there are some of you that struggle with this. So let's go ahead and work this through. If I were to say DAE, well, that's not even a triangle that we're working with. We're working with the big triangle. So I'm going to get rid of DAE, and I'm going to get rid of DAE from the other one as well. Okay. If I were to say DAC, well, again, that's not a triangle that we're working with. So I'm going to get rid of both of those from those 2. Now, DEF also is not one of the triangles that we were working with. We were working with the big triangles there, not the small ones. So if I were to say triangle CDF, okay, this triangle right here, did I read that right? CDF? That's just a straight line. That's not even a triangle itself. Okay, get that out of there. So everything's been easy so far. Okay, now I've got triangle DAF, okay, is similar to, now obviously it can't be similar to the exact same triangle, or congruent to, it can't be congruent to the exact same triangle. It's got to be a different triangle. So if I were to say DAB, that would work. Those 2 would work. However, if I were to say DAB, this one here, is similar to DAF, that one there, that would also work. So in this case, match up the correct corresponding triangles. If you go this one here, you have to go that one there. If you go this one here, then you'll have to go that one there. Just making sure you match up those corresponding parts. Okay, and that's all highlighted down here if you want to double check that. Okay. All right, now, number 18, if we go to that one, number 18, population of Florida in 2010 was 18,801,310 people, and the land area was 53,625 square miles. The population increased 5.8% by 2014. To the nearest whole number, what's the population density in people per square mile for Florida in 2014? Okay. Well, if we look at this one, the big thing is this. I think they're trying to get you trapped in the fact that the square miles increases, and it doesn't. Okay. The amount of square miles that Florida has is the amount of square miles that Florida has. Now, side note, there are some countries like Singapore and Dubai that are adding acreage to their country by bringing in sand from other deserted islands. Okay, they call it land reclamation, and Florida's not doing that. It kind of makes for it's not the most sturdy thing to do, yeah. So here's how we're going to solve this problem. We know that the population increase by 2014 was 5.8%. So what we need to do is take 5.8% of the original 18,801,310 people. Okay. Now, in order to do that, 5.8%. Remember, we're moving it 2 decimal places to the left. So as a decimal, so we can plug it into our calculator, it's going to be that right there. Of means to multiply in math. Okay. And then again, 18,810,310 people. Okay. If we do that, we're going to get this. What number is that? 1,090,000 475.98. Now I know you can't have 0.98 of a person, but I'm going to leave it there for the time being. I don't want to round to my final answer. And I'm going to add that to the original number of people that that was in the census for Florida in 2010. Okay, and if we do that, we end up with, let's see here, 19,891,785.98. Okay. Now, if we want the population density, what that means in people per square mile, they even outline it for you. It's the number of people per square mile. So I put that over 53,625 miles. This is people per square mile, okay? And we're going to get an approximation of 371 people per square mile, okay? And so as I look outside here, going from State Route 12 down County Road 9 to that first road that leads down to the elevator, you know, that full square mile right there, there might be living within that square mile, maybe 15 people, maybe a little more. I don't know the exact number of houses on the backside back there where stumps live, but at the same time, that shows you how much more densely populated Florida is than rural Ohio. For Part B, to the nearest whole number, how much did the population density in people per square mile increase from 2010 to 2014? Well, what we're going to do there for Part B is we're going to take the population density, 18,801,310, and divide that by the number of square miles. And in 2010, it was approximately 351. And so how much did it change? What was the increase? We're going to take the 371 in 2014 and minus the 351 in 2010, and the difference is approximately 20 people per square mile over those 4 years. Okay? All right. Let's just go ahead and finish out the rest of these questions here. The next question looks like this. Okay, and again, I hope you're thinking to yourself, just looking at the right triangle, you should be thinking, trig functions, not a problem. Here's what we have. Leaning Tower of Pisa is 56.84 meters long. In the 1990s, the engineers restored the building so that the angle Y changed from 5.5 degrees to 3.99 degrees. Excuse me. Why would they want to do that? Because it was probably getting to a point where it was dangerous. And how they did that, I have no idea. It would be interesting to figure that out. To the nearest hundredth of a meter, again, here we go. Make sure you're being accurate with this. How much did the restoration change the height of the Leaning Tower of Pisa? Okay, so what we're going to do is we're going to figure out this height here, okay, and then we're going to take the difference between the two. So in the very first one, if it helps, in the very first one it was 5.5 degrees, okay, and so what I'm going to do, this is the adjacent side, and this is the hypotenuse. And again, you should probably have in your reference sheet the trig function ratio. This is going to be cosine. 5.5 is equal to the adjacent, which we'll say is the unknown, over the hypotenuse, which is 56.84 meters. Okay? Now, if I solve for x here, I'm going to end up cross multiplying. X is equal to 56.84 times the cosine of 5.5 degrees. Okay? Now, they said that there was a second time after the engineers fixed it, made it a little less leaning, 3.99 degrees. Okay, so I'm going to use the exact same trig function. Cosine of 3.99 is equal to the adjacent, I'm going to make it as x again, over the hypotenuse, 56.84. Okay. Now, oh, what just happened there? Okay. Again, if I cross multiply here, I get x is equal to 56.84 times the cosine of 3.99. Okay. Now, as I do that, I want to take the difference of these two and subtract them to figure out how much did the restoration change the height of the Leaning Tower of Pisa. Okay. So if I do that, because this angle is smaller than the second one, that means that this height is going to get closer to the actual hypotenuse length. So that's the longer length. So I'm going to go ahead and do this. 56.84 times the cosine of 3.99, excuse me, minus okay, 56.84 times the cosine of 5.5. And in doing that, you are going to get approximately 0.12, okay, as your difference in length there. So, all right, finishing things up, let's go ahead and take a look at the next problem. Okay. It says Felicia wants to draw a triangle. Now I will tell you this. I picked these questions off of the Ohio Department of Education website. Okay. And so there was no way of telling exactly what they were looking for. And so I'm just going to give you the best information I have available. Felicia wants to draw a triangle PQR such that the conditions shown are true. The area of triangle PQR is not 6 square units, and the cosine of P is equal to 0.6. Use the connect line tool to draw one possible triangle PQR, then drag letters to the vertices to label the triangle. Now, this last part is actually going to be really important, and I'll show you what I mean by that in a second here. So if we're talking about the cosine of angle P, that means the adjacent over the hypotenuse. So if I go ahead and do this, 0.6 as a fraction is going to be 3 over 5. Okay. Now, again, I'm not sure what type of calculator you're going to be allowed to use on this, but you should be able to play around with the online calculator that they're going to give you and figure out that fraction, that ratio there. From there, if I go ahead and, actually let me give you a little more background information. If you didn't know it was 3/5, another way to do this is to go ahead and put this 0.6 over 1 and then multiply both those by 10. If I do that, I end up with this right here, which can reduce down to that right there. Okay. So again, that's just a way of getting that ratio. Now, if we do the cosine of angle P, let's say P is out here, okay, the adjacent side has to be 3 and the hypotenuse has to be 5, okay? So how do I draw that type of triangle here? Now, remember, this one's kind of lucky because this is a 3, 4, 5 right triangle, okay? We've talked about that lots. In the area of this figure right here, remember, it cannot be 6 square units. So if I think about this, half of 3 times 4 is 6. So it cannot be that right there. We have to change the dimensions in some manner. So I'm actually going to use this ratio right here. And if I change this up, okay, 6, 10, this is actually a 6, 8, 10 triangle. It's the same thing as the 3, 4, 5, just doubled. If I take 6 times 8, 48 divided by 2 is 24, so the area of this triangle meets this first requirement and also meets the second requirement as well. So if I mark that out, going over here, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Obviously this is 6. This is going to be 10. Okay. And this is going to be angle P. Again, you want to take that and drag it over there. P, the Q and the R, it really doesn't matter where they go. I don't see anything within the directions that had to specify which angle was the right angle. Okay. And so that's really all you have to do. You don't even have to label this is 6 and this is 10 as long as you've drawn it correctly. Okay. Now you may be thinking to yourself, what if I would have drawn it like this, 6, 8, 10? Well, it's still correct, all right, as long as you've got those 3 lengths there. So that's how you do that one right there. For the next one, okay, this one actually right here is a little bit tricky. I had to really think about this one for a while, and I'm still not sure I fully understand the last part of the question. So it says circle J is located in the first quadrant with center A, B, and radius S. So if I go ahead and draw, center is at A, comma, B, with a radius length of S. Okay, bear with me, that circle there, okay? If I was to clearly understand this problem here, this length is A, this length is B, okay? Now, the second part says this, Felipe transforms circle J to prove that it is similar to any circle centered at the origin with a radius of T. Okay, so the center here is going to be 0, 0 with a radius of T. Let's say T there. Okay. So from here it says, which sequence of transformations did Felipe use? Well, if we're going to go from here back to here, okay, the x value here, we're going to have to subtract A, and the y value here, we're going to have to subtract B to get back to this point. So what we're looking at right now as possible answers would be one of these two. We're going to take the x value and subtract the A, take the y value, subtract the B to get back to that point right there. The second part is the dilation, the factor of dilation, and this is the part are we dilating it from this circle back to this circle, or are we dilating it from this circle to this circle to show that they're similar? Whichever direction you're dilating it tells you which is your answer, C or D. If we are dilating it from this figure to this figure to show that they are similar, then you would want to take C. However, I guess I'm under the impression that if we're going from this point back to this point, we would also want to show the dilation back to that point. So I guess I'm inclined to answer D on that one between those two. So, all right, next problem. The setup of this proof is so poorly written, I don't even understand what is going on, but there is something I do want to comment on here real quickly. Let's see here. Do we have, let me pause for just a second. All right, back to what I was saying. This proof is really so poorly written, and they give no direction as to how they want you to go ahead and solve this. But there's a couple things that I think we can actually help our situation, and that's one, I've already talked about, you got to go ahead and graph this stuff out so you can start to see things, and that's where I started. When I went ahead and graphed this information out here, just do it by freehand here. I'd prefer you do it on natural graph because I think it'll make it easier for you. So we have 8, 5, Okay, so that would be Q. R is at 5, 1. Okay, there's R. And S is at 2, 5. Okay. Now remember, when it's listed PQRS, it has to be in that order. So Q is going to be connected to R, and R is going to be connected to S. Now, where's the only place that P could be located? It'd have to be up in here somewhere. Now, something to think about, if I connect those 2 points, they're on the same line right there. They're both up 5 units. We're going from 2 to 8, so this is a length of 6. If I find the midpoint, 1, 2, 3, that right there is the midpoint, okay? 3 and 3, all right? This length right here is a length of 4, 1, 2, 3, 4, okay? And we have a right triangle here, so that's nice. These lengths are going to be 5 and 5, okay? Now, I can figure out where P is going to be if I go 4 more units up. So if I go from 5, 6, 7, 8, 9, put in my point right there, that's P. Another 4 there. This is 5, this is 5, okay, because it is a rhombus. And I can get the ordered pair of P, which is going to be over at 5 and up at 9. Okay? But as far as anything beyond that, I guess the reason why I wanted to show you that problem was to make sure you understood you could actually find P. And then from there, hopefully some things will come together for you. But again, I don't like the way that this proof is written. It's confusing to me. So just do your best on those type of problems. Never leave any question unanswered because that could be points that are left out there that you could have had. All right, let's check the last problem here. Okay. In this problem right here, pretty simple problem. We've seen a couple of these where we're doing a reflection here across the line y equals x. Now, the line y equals x looks like this. Y equals 1 over 1x. Remember, that's the slope plus 0. So we first of all have to be able to go ahead and graph this correctly. Now, you'll have to play around with these points, and actually you might want to go to the website that I'll list for you and see if you can play with those points or play with this type of problem here, because I want to make sure you can actually use this program correctly. It takes a little bit getting used to, but not really. It's pretty simple. So if I go ahead and graph this at the origin, okay, slope of 1, okay, it says we have a quadrilateral as shown in the coordinate grid. Keisha reflects the figure across the line y equals x to create the new figure. Use the connect line tool to draw the quadrilateral B prime, C prime, D prime, E prime. So again, if I count this, 1, 2, 3, 1, 2, 3, there's B prime. C, 1, 2, 3, 4, 5, 6 and a half, half, 1, 2, 3, 4, 5, 6. E, 1, 2, 3 and a half, 1, 2, 3. I think I did that right. 1, 2, 3 and a half, half, 1, 2, 3. All right, so that's E prime. And then D prime, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so there's D prime. B prime. B prime. Okay. And so, obviously with the connect tool, it's going to look a lot sharper than what I just put up there. But that would be the figure to be reflected across that line there. Okay. So I hope that you understood everything that I went over. I know that was a lot. I appreciate your attentiveness, and you know, the biggest thing is I just wish you guys the best on this test coming up. So good luck to you. If you have any questions, let me know, and good night.